The night shift inherited a turbine rundown test delayed from the daytime. During the transition, reactor power dropped much lower than intended. In an RBMK reactor, very low power could produce unstable conditions associated with xenon poisoning and changing coolant behavior. Operators tried to recover power instead of abandoning the test. Later accounts often turn this into one reckless decision. The technical record is more important. The reactor entered a condition in which margins were shrinking, indicators were difficult to interpret, and the planned test procedure no longer matched the plant's actual state. Power was raised and stabilized near 200 megawatts thermal, below the level originally intended for the test. To counter the suppressed reactivity, operators withdrew many control rods. The exact count at each moment is reconstructed from records, and the later safety analysis emphasized that the operating reactivity margin became dangerously low. Yet the crew did not possess the complete post-accident model of the reactor's behavior. They were navigating a machine with known operating rules, incomplete warning about a control rod effect, and a test managers still expected to complete. Additional main circulation pumps were connected for the test configuration. Water flow increased. In an RBMK, the relationship among coolant flow, steam formation, and neutron behavior was central. More water could initially reduce steam voids and affect reactivity, while the later rundown would change that balance again. Operators adjusted controls to hold power. The reactor was not simply sitting at a steady low level. It was being held near an unstable point, while equipment configuration changed around it. Flow and pressure conditions moved outside parts of the planned envelope. Some automatic protections had been disabled or blocked to prevent the test from terminating prematurely. Not every disabled system caused the explosion, but the pattern removed layers that could have stopped the sequence earlier. Alarm signals did not present one clear message saying that the core was seconds from destruction. They described individual limits inside a complex process. The crew continued preparing the turbine rundown while maintaining power manually. Operators made feedwater and control adjustments as drum levels and flow changed. The remaining control rod margin was below the value later identified as safe. This mattered because the RBMK core was large and could behave differently in different regions. A single overall power number could hide local conditions. The reactor also had a positive void coefficient in this operating state. As water turned to steam in parts of the core, reactivity could increase rather than decrease. That feedback was the hidden mechanism waiting for the turbine test. A computer printout recorded reactor parameters shortly before the test. Later investigators used these values to reconstruct rod positions, flow, and operating margin. The printout did not arrive as a real-time verdict that destruction was imminent. Historical reconstruction must separate what data existed from what operators understood in the moment. By now, however, the plant was in a configuration where the planned rundown would reduce pump performance, increase steam formation, and interact with a core already carrying too little shutdown margin. Steam to turbine number 8 was cut off and the turbine began coasting down. Its spinning generator continued supplying power temporarily to selected pumps, the purpose of the test. As turbine speed fell, pump flow began to decrease. Less coolant flow meant more steam could form in the core. Because of the reactor's positive void response at this state, more steam could add reactivity, which increased power, which produced more steam. A safety test intended to measure electrical coast down had initiated a nuclear feedback loop. The first part of the power rise was not yet the enormous spike depicted in popular dramatizations. Parameters changed across a large core while the turbine and pumps coasted down. The unstable combination mattered. Low power, many withdrawn rods, changing coolant flow, and a design response that could turn steam formation into additional reactivity. Operators saw power beginning to rise. The exact sequence over these seconds has been reconstructed from surviving records and later calculations. No camera captured the core itself. The emergency shutdown button, AZ-5, was pressed. The reason for pressing it is not established with complete certainty. It may have been a routine end to the test or a response to rising conditions. The button was supposed to insert all control rods and shut the reactor down. Instead, the initial movement of the RBMK control rods displaced water with graphite followers in the lower part of the core. Under these extreme conditions, that design could add positive reactivity locally before the neutron-absorbing sections arrived. As rods entered, the lower core received a rapid reactivity increase. Fuel channels experienced an explosive rise in power. Water flashed into steam. Pressure ruptured channels and distorted the reactor structure, preventing rods from completing their insertion. This does not mean AZ-5 caused an otherwise safe reactor to explode by itself. The shutdown effect became catastrophic because the core had already been driven into an unstable low-margin condition. Operator actions and reactor design interacted. Removing either side produces an incomplete explanation. One or more powerful explosions lifted and disrupted the reactor structure and destroyed Unit 4. Accounts differ about the precise physical sequence and whether later sounds represented separate steam or chemical explosions. What is confirmed is the result. The core was open to the atmosphere, fuel and graphite were ejected, and fires began across roofs and debris. The explosion itself killed or fatally injured workers through trauma. Radiation would create a different emergency that responders could not see. Instruments, power supplies, and communication paths failed or displayed contradictory information. Some operators did not initially accept that the reactor had been destroyed. A reactor of that scale was not supposed to be physically gone. They attempted to restore water and understand levels using panels designed for an intact system. This was not merely denial. The control room had no direct view of the core, and many signals corresponded to equipment that no longer existed in a normal configuration. The plant fire brigade received the alarm and crews began responding. Firefighters were trained for industrial and electrical fires, not for an open reactor core scattering intensely radioactive fuel and graphite. They saw roof fires and burning material that threatened adjacent buildings and Unit 3. Their immediate mission was rational: prevent ordinary fires from spreading through the plant. The invisible radiological field transformed that mission into extraordinary personal danger. Workers outside encountered blocks and fragments around the destroyed building. Some material was graphite from the reactor. Seeing it should have implied that the core was open, but recognition was uneven and the information did not instantly reach every decision maker. Dosimeters available to many teams had limited ranges. Some instruments read at their maximum, which could be misinterpreted as the actual radiation level rather than evidence that the true level was higher than the meter could display. Municipal fire crews from Pripyat and surrounding areas joined the response. Teams climbed roofs and moved hose lines to prevent flames reaching other structures. The roof materials, cables, and bitumen created familiar firefighting targets. Reactor debris created unfamiliar exposure. Protective clothing and breathing equipment used for smoke could not shield responders from intense penetrating radiation. Yet the immediate containment of roof fires helped protect the neighboring unit and the broader station. Firefighters and plant workers received high doses while working near debris and on roofs. Early nausea, weakness, and skin effects could resemble heat, smoke, or stress. Medical teams began receiving injured people without a complete map of contamination. 2 workers died within hours from non-radiological causes. Later, 28 highly exposed workers and responders died within the first 4 months from radiation effects, according to the NRC summary. This documentary avoids retroactively assigning a dose or fate to any unnamed individual. Reports moved upward through plant and regional management, but the scale remained uncertain. Attempts continued to supply water to a reactor assumed damaged but still structurally present. Radiation readings varied because instruments had different ranges and locations. A low or saturated reading could support the wrong mental model. The information problem was now as consequential as the fire. Decisions about personnel, evacuation, and public warning depended on accepting that an event considered nearly impossible had occurred. Fire crews increasingly controlled the conventional roof fires, while the exposed reactor and graphite continued burning and releasing radioactive material. The major releases would continue for roughly 10 days, influenced by fire and temperature. The first 90 minutes did not contain the full disaster, the Pripyat evacuation or the international detection that followed. They established the conditions for all of them. A destroyed core exposed responders, incomplete measurement, and delayed recognition of the radiological scale. Chernobyl cannot be explained honestly as a foolish crew pressing the wrong button, or as a perfect machine betrayed by operators. The test proceeded in a reactor state outside safe margins. Operators made consequential choices. The RBMK design produced dangerous feedback at low power and a shutdown rod effect that was not adequately communicated. Protections had been weakened, and the emergency response lacked instruments and assumptions for an open core. In 90 minutes, those layers aligned. The lasting lesson is not that one action destroyed Reactor 4. It is that a safety system failed at design, procedure, communication, and emergency recognition simultaneously.